Okay, so here we go, part two of this section three, if you will. Back to the official or precise definition of the limit, right? So this is exactly the same. The limit as x approaches a of f of x is L. What does that mean? Well, it means we can make these two things super close. How close? Well, within epsilon close. Okay, how do we do that? We have to get close enough to a with x. So again, for all epsilon greater than 0, given any y window, no matter how tiny it is, there has to exist an x window such that if you're in the x window, you're guaranteed to be in the y window. Okay, that's essentially what this definition is saying. Okay, so given, let's do a specific example. Let's say we're given y equal x squared. I want to find a delta such that I'm in plus minus this 1/2, okay? So this is obviously our epsilon. If we look at the definition above, this is obviously our limit, L, okay? And as it turns out, this is also our A on the x-axis, okay? So setting up this picture, here's what we get. So we're saying here that our epsilon is 1/2. So if we go plus minus, we know that the limit as x approaches 1 of x squared minus 1 is obviously 1, right? That's a, oh, sorry. No, as x approaches 1 of x squared. Wait a second. Sorry about that. It's x squared, not x squared minus 1. Apologies. Let me restate that. Getting ahead of myself. Okay, so we know that the function is x squared. That's f of x, right? So we know that the limit as x approaches 1 of x squared is 1. Sorry, thank you. That's direct substitution. That's not really the question here. We're kind of getting into the definition, the precise definition. We're trying to find a delta that works. So here, if this is 1 and epsilon is 1/2, we have to go plus minus 1/2. So we go up to 1.5 and down to 1/2. That's our window. That's our y window. And the idea is, well, what's the x window here? And again, you can back sub this. Okay, so if y is 1.5, so f of x, right, is x squared. So if it's 1.5 is x squared, what's x, right? And if f of x is 0.5, what's x, right? In other words, I'm looking for these values here and here, and you have them here. One of them is the square root of 1/2, because obviously squared, that's 1/2, and this is the square root of 3/2, obviously squared is 3/2. So we can kind of figure that out. Now we need to find these deltas, and so we need to find these two distances. So I have this distance here, and I also have this distance here. And notice, because this is not a linear function, it's a curve, they're different. Okay, so the gray distance here is 0.292, and the green distance here is 0.224. And that does make sense, because obviously the gray looks a little bit longer than the green. So I take a look. So on one side it's 0.292, the others are about 0.224. So remember, you can only have one delta. Okay, so which one of these do you think would work? Okay, or would they both work? Well, it turns out they will not both work. The only one that will work is the 0.224. If you chose the gray as your delta, you'd be fine on the left, but that same distance would kick you outside of the window, okay, on the right. So it's no good. So you have to take the smaller of the two, because this is on the window, and then that same distance here will keep you well within the window that we're looking for on the y-axis. Okay, so you can kind of figure this out working backwards. So you always have to pick the more restrictive or the smaller of the two. Okay, it has to work on both sides. You don't get to say, well, on this side it's this, on this side it's the other. Okay. All right, so now let's get into an actual definition. How do you actually prove that this is the case? Yes, of course, we can use direct sub and figure it out, but why does direct sub work? Well, direct sub would only work if you were able to prove it, so that's what we're going to do here. Now, let me show you how this works. Again, we'll do a few linear functions. Those are pretty straightforward. And then we'll do one that's not, and those are a little more interesting, but not super awful. So you want to work backwards. So again, the idea is to use the definition and go backwards. So for all epsilon, there has to exist a delta such that x minus a less than delta implies f of x minus l is less than epsilon. So we need to get, this is our result. We need to make that happen. So what you want to do is start with what's called some scratch work, okay? And the scratch work always starts with, I need this to happen, okay? So what is my f of x minus L in this particular case? Well, this is f of x, and that's L. So that's the absolute value of f of x minus L. So combining that, I get this, and then notice I can take a 4 actually out of both of those items, and the absolute value makes them positive, and so that ends up being equal to this. Now when I get here, and I can drop the absolute values, because the absolute value of 4 is 4. Now when I get here, I'm happy. Why am I happy? Remember that what's the one thing you get to control or you get to make as small as you want? This part here, you get to make as small as you want, okay? Now, what is delta, right? It's x minus a. So in this particular example, what's x minus a? Well, it's the absolute value of x minus 3. So when I see that show up in my scratch work, ta-da, I'm actually happy. Why am I happy? Because remember, in order to do this in general, your delta is going to have to be based on your epsilon, okay? So what do I notice here in this green box? I notice that this, remember, what did we start with? We started with f of x minus L, and we notice that f of x minus L is actually equal to 4 times delta, right? Because x minus 3 absolute value is delta. So if f of x minus L is the same as 4 times delta, what do you think I can use to figure out delta? Well, I can just take the epsilon and divide it by 4, okay? So I stopped when I got this because that's the delta part, and I can make that as small as I want. So this will work. Technically, this will work, or anything less will also work, right? So if you want to be cute and say for this problem, let delta be epsilon over 10, that's fine, still works. You don't have to land exactly on the endpoints, you just have to be within inside it. Or sorry, excuse me, you just have to be inside it. So how do you formulate the proof? So again, the proof is based on, given this epsilon, here's the delta that works, and this is the reason why. So this part here is the actual proof. Given any epsilon, choose delta to be epsilon over 4, or again, anything smaller is fine. Then you have to show why it's true, because if the absolute value of x minus a is less than delta, what does that imply here? Well, it implies that f of x minus L, which is equal to this, which is equal to this. You already did that in the scratch work. Now notice that this 4 and this 4 are equal, and notice that this statement here says that x minus 3 is less than epsilon over 4, because that's what we're saying above. And so you can use the less than sign and replace the delta with epsilon over 4. These then cancel and you have your epsilon. So the important thing here is, what am I saying? Well, what I'm saying, let's clean up this mess that I have for just a second. What I'm saying is that if this is less than delta, f of x minus L is less than epsilon for any given epsilon. So this is just a summary. You don't actually need this, and that just signifies end of proof. That's kind of the new way to do it. The old way was QED, which is Latin, and it translates to as was to be shown. Anyway, I don't care which one you do. But I do care that this part's correct. So you can now actually, like I have here, you can try this with values. Okay, our claim is no matter what epsilon, no matter what y window you give, divided by 4, that x window will work. So let's say I want to get within 0.001, right? So my claim is divide that by 4, and it should work. So 0.001 gives me what kind of an interval? Well, gives me 6.999 to 7.001. Now our proof claims divide that by 4 and it works. That's divided by 4. So that means plus minus 0.00025 on the x-axis, which is this, should work. Let's see, right? What if you plug in f of 2.9998? Is that in the window of this delta? Yes, it is. What's the output? 6.9992. Is that in this? Yes, it is. Okay, it is. Okay, it works. What if we go outside the interval, right? Well, then you see that it's outside of our window. So you can actually plug in some values there and check this out. It's actually, I do think it is moderately neat. So let's do another one of these, and then we'll kind of go through the more complicated one. And then we'll be good with this section here. So again, you can see this is a straightforward limit to evaluate, but we're going to do the proof, which means delta epsilon like we did in the last example. You can also see that it's a linear function. So we could probably guess that, right? Once you do a few of these, you can look and say, oh, it's a linear function with slope 2. It's going to be an epsilon over 2 proof. Yes, fine, no problem. We'll go through it. Again, start with your scratch, f of x minus L, which in this case is 2x plus 3 minus 5. Again, as I'm doing this, what am I hoping shows up? Absolute value of x minus 1, because that's x minus a. And lo and behold, oh, look at that, we factor out a 2. And again, so divided by 2, it's an epsilon over 2 proof, as I said earlier. Okay, and so then you formulate the proof, right? Given any epsilon greater than 0, choose delta to be epsilon over 2 or less. If you want to do epsilon over pi, get some slick bonus points, that's fine. Epsilon over 2 works. And then you show why it's true. Because if absolute value of x minus 1 is less than delta, f of x minus L is less than, right, 2 times delta, which is this, and you're good to go. Okay, that's what you wanted to show. Again, you can try actual values with this, and it certainly will work. Okay, so here's the last part that we'll go through here, and already we can see this is a problem. It's a problem because it's not linear. So in my scratch, what am I going to be looking for? Well, the absolute value of x minus a. So I'm looking for an absolute value of x minus 3. So, sorry, I look at f of x minus L, which is absolute value of x squared minus 9, which factors into these two things. You have to keep the bars there. And so I got my x minus 3 right here. Lovely. But I also have this extra part here with, what? So are we going to say that delta is just epsilon over x plus 3? No, can't do that. Okay, it has to be no x values in there. It's not going to work. So how do we deal with this? Well, we deal with this as follows. Okay. So yeah, this is no good. So here's what we deal with. Let's see how I want to do this. Let me take a little piece of white over here. Okay, so I'm going to go through now what the notes are going to explain. So just bear with me. For now, let's assume that, again, this statement means what? This means we can make x squared and 9 as close as we want by picking values of x close to 3. So we mean close to 3, right? We don't mean plus or minus 35. We mean, like, let's say plus or minus 1. So let's take a look for a second, and let's restrict it to within 1 unit of 3. So that's between 2 and 4, yes? Okay. Now, this is the problem here. I don't know what to do with this. I need to, the magic word is bound. I need to bound this. Okay? In other words, make it less than some constant. Make x plus 3 absolute value less than some constant. If I can bound it, I can deal with it. So let me show you how we do this. So let's consider within 1 unit of 3. That's between 2 and 4. So if x is between 2 and 4, what does that say for x plus 3? Well, that's obviously between what? Adding 3 to everything would be 5 and 7. Really, I'm not trying to bound x plus 3. I'm trying to bound the absolute value of x plus 3. So if I put in x plus 3 absolute value, what number do I need to put in here for C that satisfies all the values between 5 and 7? Notice that 5 will not work. Okay, if x plus 3 absolute value is less than 5, that means x plus 3 is between 5 and negative 5, and that does not cover all the numbers between 5 and 7. Okay, so this will not work. If, however, I choose my constant to be 7, that means x plus 3 is between 7 and minus 7. Does that cover all of these values here? Yes, it does. So you can actually pick, let's see, B7 or more. 10 would also work. Okay. So we found a constant to bound this. However, this constant was specifically built on what premise? It was built on the premise that we are within 1 unit of 3. If you're not within 1 unit of 3, this 7 is useless. So now we actually have 2 restrictions, okay? We have the delta, regular old run-of-the-mill delta restriction, which we always have, and now we need to be within 1 unit. So do you remember with the x squared example earlier, there were 2 options. On one side it was like 2.92, the other side was like 2.224, something like that. You had to pick the smaller of the 2. We have to do the same thing here. So this is a bunch of explanation of what I just talked about. I found the same constant, which was 7. So, excuse me. So we have to proceed carefully here because we have the 2 restrictions. We have our constant 7, and then we need the epsilon over 7 if that ends up being our constant. But this constant was built on within 1 unit, okay? So to ensure both of these restrictions are met, you have to choose the smaller of the 2. How do we do that? We use this notation right here. min1 / epsilon over 7. Okay, that means smaller of epsilon over 7 or 1. The reason you need this in here is if some clown gives you a huge epsilon like 14, right, then and you just left it as epsilon over 7, then epsilon over 7 would be 2, and that actually wouldn't work because this says you have to pick the smaller of 1 or epsilon over 7. So if someone said epsilon is 14, you pick the smaller of 1 or 2. You have to actually pick 2. Delta would be 1 in that case. It wouldn't be 2. Okay, so you have to pick the smaller. You need that in there. Okay, so now we say same sort of proof, right? Given any epsilon, choose delta to be the minimum of these 2. Okay, then if x minus 3 is less than delta, f of x minus L, which is equal to that, is less than 7 times epsilon over 7, and we're good to go. Here's an example to show you where if epsilon is 14 and you don't have that minimum in there, it'll fail. Okay. Actually, it's not in there. It just says try it, so you go ahead and do it. Okay, so here's the worksheet. This is a specific one. This is delta epsilon with linear, so it shouldn't be too big of a deal. And then here's the homework for you. And now we're up around almost 18 minutes, so we're gonna cut it off here.